Okay, we are live again. Let me just check out everything first. Okay, everything's working fine. I'll just update in all the groups. Done. Okay, so I'm gonna wait for like 4 more minutes because I've already waited for like 1 minute right now. I'm gonna wait for 4 more minutes so that everybody can have a chance to join in, and then we'll start. Okay, done. Yes, 2 minutes down. Okay. So here, now the problem that we're going to do is basically called as something like LCA of a BST, and this is lead code problem number. I haven't seen the problem number yet, so I'll update that later. And now we're going to solve this problem. Okay. Hi Siddharth Verma, how are you doing? Okay. तो यार अब बेसिकली सीन कुछ ऐसा है कि एवरीबडी इज गोना थिंक दैट सर व्हाट एक्चुअली इज LCA, व्हाट एक्चुअली इज अ BST. सो बाय LCA here we mean lowest common ancestor, and by BST we mean binary search tree. Okay, it's binary search tree. Okay, so here now what actually is a binary search tree? In a binary search tree, if you have a tree something like this, something like this. So anything on the right is going to be greater than anything on the left. What do I mean by that? The element inside this element is going to have different elements down the nodes. So anything on the right is going to be greater than this element, and anything on the left is going to be smaller than this element. And now similarly, if you talk about this, anything on the right of this will be greater than this element, and anything on the left of this will be smaller than this element. But we are going to consider that anything over here in total is greater than this element. Are you understanding? So anything on the right is greater than anything on the left. Okay, let's see an example. I'm just going to give you an example right now. Let's go. So now the example is, imagine we have 6 over here. So anything on the left of 6 is going to be anything is going to be less than anything on the left of 6 is going to be less than anything on the right of 6. So let's see, we have 2 over here and we have 8 over here. 9, 7, again we'll have 0, we'll have 4, we'll have 3, and we'll have a 5. So now let's see what are we fulfilling over here. If this is 6, 8, 7 and 9 are greater than 6. Considering 8, 9 is greater and 7 is smaller. Considering 6, 2, 0, 3, 4, 5, everything is smaller than 6. And now let's see 2. So 0 is less because it's on the left and 4 is more because it's on the right. Here 3 is less than 4 and 5 is greater than 4. What is the problem? We have to find the LCA over here, the lowest common ancestor. Understood? We are going to find the lowest common ancestor. So everybody understood what a binary search tree is? Tell me, everybody understood that? So how are we going to get the problem? We're going to get the problem like LCA of 8 and 9. Or maybe LCA of 7 and 9. So the lowest common ancestor of 7 and 9, if we calculate, is we iterate throughout the binary search tree and I see the lowest common element on which 7 and 9 are connected is this. Because if you see, this is the first connection, this is the first connection, and here. Similarly, 6 is also an ancestor of 7 and 9, but the lowest common ancestor is 8. Understood? So this is the entire problem. Did you guys understand? A very simple, direct problem. But how do you do that? Tell me. We have 3 observations over here, or maybe we can make it 2. Tell me one thing. If you iterate on the right side and you check if 8 has any number less than itself, which is 7, and is there 9 on the right of 8. So try and understand something, that when you iterate and you check for 7, that where 7 is on the left, and where 9 is on the right. So the first place where you split up your iteration, if you're coming from this place, when you have to split up, that is the lowest common ancestor. Let's take a little bigger example for the same. I'm going to make a bigger tree. Okay, it's back. And the reconnection is successful. Done. I'm so sorry. The stream got disconnected because of my Wi-Fi, not my fault. I'm so sorry. So we'll have 6 over here. For 6, we'll have 5. We'll have 7. And for 8, we'll have 9. So just look at this tree and see if everything is in the order of a binary search tree. And now what I'm going to do is iterate for 5, 9. Okay. So I go over here. I see the number is 4. So I know that both 5 and 9 are going to be on the right. Then now I come over here and I see the number is 8. So I know that 5 is going to be on the left and 9 is going to be on the right. Means here is the path where we are splitting up. So this is my LCA. But now I want to ask you one thing, that what if rather than 5, 9, I start searching for 1, 2? If I search for 1, 2, I'll check for 10. So both 1 and 2 are on the left. I check for 4, both 1 and 2 are less than 4, so they are on the left. I check for 3, both 1 and 2 are on the left. But here I check for 1 and 2. For 1 I do not get a position because 1 is the place where I am. When 1 is the place where I am and I do not have a left or a right position for any one of the elements, means that we are on that very element. And if we see, the first ancestor where 2 and 1 are connecting are 1 itself, is 1 itself. So basically 1 itself is the LCA in this case. Understood? So here is the test case, or here is the LCA, wherein is in this test case we have 1. Now what if I ask you the time complexity over here? What do you think is going to be the time complexity? Tell me. Tell me, what do you think is the time complexity over here? Tell me. Any guesses? Okay, so Lalit says it's big O of n, but Lalit, if I ask you how many elements are there in this tree? Simple. How many elements or how many nodes are there in this tree? The number of nodes over here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But this is for sure that we are not going to, wander around all the 13 or, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. No, it's not 15, Lalit, it's 13. The number of elements is 13, but I am only traversing throughout the single side. So it's kind of the height. In the worst case, it's going to be the height of the tree. So I can say if h is the height, my time complexity becomes big O of h, and the space complexity is big O of 1 if I'm not using a recursive function, or if I am excluding the stack space required or the auxiliary space. The big O of the space complexity comes out to be big O of 1, and it becomes big O of h, considering h is the height of this binary search tree. So the basic idea behind choosing this problem is the time and the space complexity, because iterating and all that is normal, but actual gist of the problem lies in the time and the space complexity. Okay? Understood? Okay, so I hope it was simple. I hope it was easy to understand. And now we are gonna end the stream. I will be streaming tomorrow. Tomorrow we are gonna do 2 problems, and I'm gonna do 2 C++ streams. And Saturday, Sunday I'm not gonna stream anywhere at all because I have some things to take care of. So Saturday, Sunday no streams. Tomorrow we'll have 2 problems and 2 C++. Okay, thank you so much for joining in, guys. See you guys tomorrow. Have a nice evening.